Okay, so in this video, this is the problem 13 from final May 2015, if I'm not mistaken. Here we're going to do another problem from vector geometry. The problem says given the points A, B, C, and D, and then we have a list of questions here. Okay, so as always, you can pause this video, copy down the questions, and try to solve them first by yourself, and then check your answers with my solutions right here. So what are you given? What are you asked? Sorry, you're asked to find the equation for the line containing the points A and B. Part B, you have to find the distance between the point D and the line that we have found in A. In part C, we have to find the point on the line from part A that is closest to the point D. Then we have to find the area of the triangle with vertices A, B, and C. Part D, we have to find the equation of the plane containing the points A, B, and C. And finally, we have to find the volume of the parallelepiped determined by the vectors A, B, A, C, and AD. Okay, so let's start from the beginning. First of all, let us find the equation containing the points A and B. So right away we know what is the parametric equation of a line x, y, z is equal to x naught, y naught, z naught plus t times the vector a, b, c. So this represents a line, this is the point. So, sorry, the other way around, this is the point. And this is the vector parallel to the line. Okay, so if we have 2 points A and B, you can choose either A or B to put it in here instead of the point, right? And then what vector is going to be parallel to this line? Well, the vector AB or the vector BA, depends what you want. So let us take the point A with coordinates 5, 2, and 0. And we have to find the vector AB. Okay, how do we find AB? Well, we subtract the entries of the vector A from the vector B. So that's 7 minus 5, 7 minus 5, 0 minus 2, 0 minus 2, and negative 2 minus 0. So the vector AB is 2, negative 2, negative 2. Okay, so what do we have? I have a point on the line, A, and I have a vector parallel to the line, that's the vector AB. So now you just come back here and you write that xyz is equal to 5, 2, 0. One more time I'm repeating, the point on the line plus the parameter t, that's why it's called parametric equation, times the vector parallel to the line, and we found that one, 2, negative 2. Negative 2. Okay, let's call this line L. Let's say that this line in part A that passes through A and B, it's called the line L. Okay, so we move on to the second question. Find the distance between the line found in A, find the distance between the line found in A and the point D. Okay, so now we have here A and B, okay, and the point D. I want to calculate how much is this distance. Okay, so what can we do? Well, we're going to do this using projections. First, I'm going to determine what is this vector here, the vector AD, and I'm going to project that vector onto the vector parallel to the line. In other words, I'm going to project this vector AD onto the vector AB. That will give me this vector right here. Okay, so this is going to be the projection of the vector AD onto the vector AB. Okay? If you're not given a particular point on the line, as we are given right now, you can find a particular point on the line just by choosing any t that you want. Okay, so for example, if we choose here t is equal to 0, then indeed I'm going to obtain the point A. Once we find the projection of the vector AD onto the vector AB, that's this vector right here, their difference is just going to be this green vector right here. Finding the magnitude of that vector gives us the distance between the point D and the line passing through A and B. Okay, so let's start from the beginning. Let's first find the vector AD. So that's the coordinates of the vector, of the point D. So the entries of the vector D, 4, 3, 4, and then we subtract A, 5, 2, 0. So this vector has entries negative 1, 1, 4. Okay, and let's call this this vector here V, the vector V. Okay, and let's call the vector AB U. Just because, just in order to simplify this notation right here, that was the vector 2, negative 2, negative 2. Okay, so first, what are we going to do? We're going to project AD onto AB, so that's the projection with the new notation. That would be the projection of V onto U. And now the definition of this vector is V dot product U over U dot product U. This is a scalar and this is a scalar, so the ratio is going to be scalar times the vector U. Okay, so on the side, very quickly, I'm going to calculate these two dot products. V dot product U, that's negative 1, 1, and 4, dot product 2, negative 2, and negative 2. So we just multiply the corresponding entries, and then we sum up these values. So that's negative 1 times 2, negative 2, 1 times negative 2, negative 2, 4 times negative 4 is negative 8, and that's negative 12. Okay, and U dot product U is 2, negative 2, negative 2, dot product 2, negative 2, negative 2. That's 4 plus 4 plus 4, and that's positive 12. Okay, so here we have V dot product U is negative 12 over U dot product U is 12 times the vector U, 2, negative 2, negative 2, which is equal to negative 1 times 2, negative 2, negative 2. So this means that implies that the projection of V onto U is equal to the vector negative 2, 2, 2. Okay, so that is this vector right here. This vector is the vector negative 2, 2, 2. As you can see, is parallel to the line as we expected. Okay, so now the difference between the vector AD that we called V, the difference between this vector and the projection gives us the vector, the green vector right here, whose magnitude gives us the distance between the point and the line. Okay, so first I want to find the difference between V, that's AD, right, this, minus the projection of V onto U, so that V is how much? Negative 1, 1, 4, minus the projection, which is negative 2, 2, 2, and that's equal to negative 1 plus 2 is 1, 1 minus 2 is negative 1, and 4 minus 2 is 2. So this vector right here is this green vector. When we're going to find the magnitude of that vector, we'll get the distance. Okay, so we just find the magnitude here. That's equal to square root of 1 squared plus negative 1 squared plus 2 squared. That's square root of 1 plus 1 is 2 plus 4, that's 6. So the distance between the point D and the line passing through A and B is square root of 6. Okay, the next problem, part C, says find the closest point from the line L, the line found in A, right? So this is A and B, and this, we call this line L, and here was the point D. So now what are we looking for? We're looking for this point right here, okay? Where the line crossing through that point and D is orthogonal to any vector parallel to the line L, okay? So what do we know? First, we know the equation of the line going through A and B. We found that on as the first question. So that's x, y, and z is equal to 5. What was it? 5 to 0 plus t, and the vector was 2, negative 2, negative 2. Okay, so let's say that this point right here that we're looking for has the coordinates x, y, and z. Okay, because that point lies on this line, it has to satisfy this equation. That means that x is going to equal to 5 plus 2t, y is going to equal to 2 minus 2t, and z is equal to negative 2t. Okay, so I have set of 3 equations with 4 unknowns. Okay, I cannot solve this, so I need some extra condition here. That condition comes from the orthogonality. Okay, the vector between this point with coordinates x, y, and z and the point D, okay, let's call it W, is going to be x minus, right, so this vector here, the coordinates of D, so x minus 4, y minus 3, z minus 4. So that's some vector W right here. And now this vector W is orthogonal to the vector parallel to the line. And the vector parallel to the line was 2, negative 2, negative 2. It's parallel to the vector. Did we give it a particular name here or not? We called it u. Okay, so this vector W is orthogonal to u. This implies that W dot product u is equal to 0. So let's see where this is going to lead us. This is x minus 4, y minus 3, z minus, why is this z here? 4, sorry, my bad. Minus 4, dot product u, and u was 2, negative 2, negative 2, has to be equal to 0. And let's perform this dot product. 2 times x minus 4 is 2x minus 8. Negative 2 times y is negative 2y. Negative 2 times negative 3 is plus 6. Negative 2 times z is minus 2z. Negative 2 times negative 4 is plus 8 is equal to 0. Okay? So let's solve this. 2x minus 2y minus 2z, this and this cancels, is equal to negative 6. We can simplify this by dividing by 2 both sides, and I have x minus y minus z is equal to negative 3. Now, this is satisfied for the point x, y, and z. On the other hand, the point x, y, z, for that point, the following is satisfied, right? So what if we plug this x, y, and z in terms of the parameter t? Here I have 5 plus 2t minus 2 minus 2t minus z is negative 2t is equal to negative 3. And what do we have? An equation with one unknown. That's easy for us to solve. 5 plus 2t minus 2 plus 2t plus 2t is equal to negative 3. 2 plus 2 plus 2 is 6t is equal to 5 minus 2 is 3, bringing on this side negative 3 minus 3, so t is equal to negative 1. So we have found a parameter that satisfies this parametric equation. Plugging that into the parametric equation right here, we'll find the coordinates of the point. So x is equal to 5 plus 2 times negative 1, that's 3. Y is equal to 2 minus 2 times negative 1, that's 4. And z is equal to negative 2 times negative 1, and that's equal to 2. So this point right here, the point that's on the line L and closest to the point D, has coordinates 3, 4, and 2. Next problem, we have to find the area of the triangle with vertices A, B, and C, so part D. Okay, so we are given A, B, and C here, and what do we know? That if I find the magnitude of the cross product AB and AC, that will give me the area of this parallelogram. Okay, so the area of the parallelogram is equal to, of course, the absolute value of the norm of the vectors, cross product of the vectors defining that parallelogram. Okay, so I have AB. The vector AB is 2, negative 2, negative 2. The vector AC is negative 3, negative 1, 1 minus 0 is 1. Okay, and now I have to find the cross product between these two vectors. Okay, so AB cross product AC is equal to IJK. Here I have 2, negative 2, negative 2, negative 3, negative 1, 1. And I find the determinant of this vector. So this is I minus J plus K. And I solve this by finding the cofactor expansion about the first row. So that's negative 2 times 1 is negative 2 minus negative 2 times negative 1 is just 2. Minus, don't forget about this sign, 2 times 1 is 2, minus negative 3 times negative 2 is 6. And the last one is 1 times negative, 2 times negative 1 is negative 2, minus negative 3 times negative 2 is positive 6. Okay, so this cross product is equal to the vector with entries negative 4. This here is negative 4 with negative in front, positive 4, and finally negative 8. Okay, if we find the magnitude of this vector, so if we're now looking for the magnitude of this vector, that's square root of 4 squared, sorry, negative 4 squared plus 4 squared plus negative 8 squared. That's 16 plus 16 plus 36. And, 64, my bad. That's square root of 32 plus 64. That's square root of how much? 96. Now 96, if I'm not mistaken, is square root of 16 times 6. So the magnitude of this vector is equal to 4 times square root of 6. So 4 times square root of 6, right, is the area of the parallelogram. But we will not ask the area of the parallelogram, we will ask the area of this triangle. Well, the triangle is just what? Half the area of the parallelogram. right? So the area of the triangle described by these two vectors is just 1/2 times the area of the parallelogram defined by these two vectors. So our answer here is going to the area of the triangle is equal to 1/2 times 4 square root of 6, and that's 2 square root of 6. Okay, so next question says find the equation of the plane containing A, B, and C. So part E. Find the equation of the plane containing A, B, and C. So I have some plane here, right? The equation of the plane is calculated by solving this dot product x minus x naught, y minus y naught, z minus z naught is equal to 0. Okay, so x naught, y naught, and z naught are the coordinates of any point on the plane. Okay, we're given 3 points, so you can choose whichever you prefer. And n is the normal vector to the plane. Okay, so if we choose the point A for let x naught, y naught, and z naught just be the point A, right, which was given by 5, 2, 0. And now we have to find the normal vector. Well, the normal vector, if A, B, and C lie on this plane, then the vectors AB and AC lie on this plane, right? The idea of the normal vector, of the cross product, is that the cross product gives you a vector that's orthogonal to every single vector on the plane. Okay? So if we find the cross product of AB and AC, that will give us the normal vector AB cross product AC, but this was already calculated in the previous problem. That was -4, 4, and -8. So there you go. I have a point and I have a vector normal to the plane. So now I just solve this equation here. N dot product x minus 5, y minus 2, z minus 0 is equal to 0. The vector is -4, 4, -8. Dot product x minus 5, y minus 2, z is equal to 0, and then just expand this and solve this, calculate this dot product -4x plus 20 plus 4y minus 8 minus 8, z is equal to 0, so -4x plus 4y minus 8, z is equal to -12, and you can leave it here, or you can just divide by -4 everywhere, so x minus y plus 2z is equal to 3. And the last part of this problem is finding the volume of the parallelepiped determined by the vectors AB, AC, and AD. So again, I have the vectors AB, AC, and then D does not lie, at least I hope, doesn't lie on the plane described by these two vectors. So this is D, okay? So this base here is formed by the cross product, and then this goes out in 3 dimensions, right? So I have to find the volume of this parallelepiped. Now, as one of your classmates reminded me, we did the volume of, we said that the volume is equal to the absolute value of U dot product V cross product W. But then if you remember when we did the determinants, you can find the volume, and this can be proven that it's the same as the determinant, the absolute value of the determinant of the vectors, so sorry, the determinant of the matrix having the columns U, V, and W, and here the absolute value of that. Okay, so we have the vectors A, B. Again, I keep on forgetting this. 2, negative, 2, negative, 2. Let me just, so 2, negative, 2, negative, 2. A, C, which is the vector negative 3, negative 1, 1, and the vector AD, which is negative 1, 1, so negative 1, 1, 4. Okay, so the volume is going to be the absolute value of the determinant of the matrix having these 3 vectors as columns, and by properties of determinants we know that we can put them as columns or as rows. That's not going to affect the value of the determinant. So the determinant of the matrix 2, negative 2, negative 2, negative 3, negative 1, 1, and negative 1, 1, 4. So that's the absolute value. We know that if we add multiples of one row to another, it's not going to affect the value of the determinant. So what do I do here? I add the second and the first row, and the third and the first row. So the first row is 2, negative 3, negative 1, negative 2 plus 2, 0, negative 1 plus negative 3 is negative 4, and 1 plus negative 1 is 0, negative 2 plus 2 is 0, 1 plus negative 3 is negative 2, 4 minus 1 is 3. And now I can do a cofactor expansion along the first column here. So I have 2 times the determinant of this submatrix, negative 4, 0, negative 2, 3, which is equal to 2 times negative 4 times 3 is negative 12 minus 0 in absolute value. That's absolute value of negative 24, which is equal to 24. Okay, so the volume of the parallelepiped can be determined by solving by evaluating the determinant as the fastest way, the determinant of the matrix formed by these 3 vectors, where the columns or the rows, as we said, are just the vectors describing the parallelepiped, sorry, not parallel, volume of parallelepiped.